What's up, people? AP Physics people. What's happening? Um, it's Tuesday afternoon. I'm operating under the assumption that in the 40 minutes we spent together, that we're spending together tomorrow, Wednesday, we've started this. This is an introductory, maybe 2-day thing, which means we have a quiz pretty soon, probably Monday or Tuesday of next week. Introductory thing about different kinds of quantities that we're going to talk about. We'll talk about tons and tons of different physics-based quantities. But there's a major distinction between them we need to be able to draw. And we can start to address that distinction by answering this question. The question is, does walking 10 miles always take you 10 miles? Now, I need to do this. Yeah, good. And, yeah. So there's the question. Does walking 10 miles always take you 10 miles? And I hope we came up with this answer earlier. Oh, the answer is no. First of all, the answer is no. Because if some of you said, well, what if I walked, 5 miles this way, and then I walked 5 miles this way, has it taken me 10 miles? I guess you could argue that it has. I have traveled 10 miles, but if I started here and ended here, then I really haven't traveled anywhere. So it really depends on how you want to address it. The answer to this is kind of yes, it's kind of no. And there are other things that work this way, other kinds of quantities that work that way. These quantities that we're talking about here, these are what we call distances, but we'll put that in quotes because there's something else we can refer to them as if we want to get a little fancier. And we're going to get a little fancier. All right? So, sometimes walking 10 miles at certainly a distance does take you 10 miles. Sometimes it doesn't. And there are other quantities we can substitute in here instead of distance that we can illustrate this same point with. All right? And what this gets down to is the difference between, or a major difference in different kinds of quantities or things we can measure in physics. All right? What we can say is we can break up anything into one of two camps. Everything that we measure is either a vector or a scalar. Does that work anymore? I got this clicker here. It doesn't seem to work. Yeah, so what's the difference? All right, well, scalars. Scalars are the simpler of the two, and scalars include what we call a magnitude element. All right, magnitude means amount, whoops, or size, or value. And then there are vectors. Vectors, because they're quantities, all quantities do have a magnitude. All quantities have to have some sort of amount of something, and the big deal is and direction. All right, you'll notice in the page before, I said, well, what if I walked 5 miles this way and then walked 5 miles that way? The act of me saying this way or that way means I'm talking about a vector quantity. Okay? So all vectors, notice I said 5 miles, and then I said this way, or that way. All right? Or I really should say, like east or west. Okay, I'm using both of those things, the amount of how far I went and the direction of where I went. Oh, now, let's write down some examples. So things that are scalars. It might be, things that are scalars and things that are vectors. I'm going to ask you to write this. Give me some examples of each. Think of things you can measure. And you say, well, I don't know what we're going to measure in physics. You probably do, a few things at least. And see if you can put them in either camp. And I'll give you a hint. And again, I don't care if they're physics things or not. You can take things you measured in chemistry. Take things you measured in earth science or biology, or things you think you might know from physics. And don't just go looking these things up. Some of you are just going to Google vector versus scalar. Boring. Think. Think for yourself. So what I want you to ask yourself is this question. I'll say, question. Does saying, it says saying, does saying that way after quantity, yeah, sure, makes sense? Well, yes, it's a vector. No? It's a scalar. And here's what I mean. Let's see, what's something you measured in chemistry? Oh, I got one. Volume. Volume. You can measure volume in liters, right? You can say, okay, how much water do I have? I have a liter of water. So, does it make sense to say, I have a liter of water west? That makes no sense. Therefore, which one is volume? Not that makes volume. Scalar. So think of other things you can measure. If you can say, because some things it does make sense to say, well, we just did it a minute ago, right? What if I say 5 miles that way? That makes sense. There's nothing wrong with saying that. Well, that makes whatever we call this, that quantity, unfortunately, it's not distance. Well, that's a vector. So I'm just going to say 5 miles east, right? 5 miles east. That is a vector. All right. Now, what I don't want you to do is don't just say, well, okay, what if I said 10 inches west? Is that a different one? That's not a different one. You're still measuring how far something goes and what direction. So come up with different things you can measure. They're going to have different units. Different units. Now, the problem is we might have already done all this in class. Oh, well. Next. Now, the thing about all vectors, because all vectors have a certain size and go in a certain direction, there's a nice simple drawing we can make that represents any vector quantity, no matter what kind of vector quantity it is. And that simple drawing is, well, that is what we call a graphical, or a drawing of a drawn vector, a graphical vector. Notice, it has a magnitude, it has a size, right? Well, the length of this thing the length of it, that little symbol, which is an alpha, means is proportional to the magnitude of the vector. And, based on, I don't know, maybe what this angle is, that angle, what we call theta there, that tells something about direction. So that vector is very different from that vector. Well, they're different because even though they point in the same direction, they have different magnitudes. Right? It's different from this vector because the magnitudes and the directions are different. You got me? Now, how do I tell what kind of vector quantity this is? Now, we're going to tell by using a scale. For example, I could say something like, every centimeter of length of that vector represents, I don't know, let's say 10. Well, let's do this. Kilometers. Now, if I were to use a ruler, I could measure how many centimeters long that vector is, and therefore using this proportionality, scale, notice we said the length is proportional to the magnitude of the vector. We could say, all right, if it's an 8 centimeter long vector and every centimeter represents 10 kilometers, that means, well, that represents an 80 kilometer displacement. And I could use a protractor and measure this angle, and then if, maybe I had something like this where that's north, oops, and that's south, and blah, 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 I could say, oh, that's 30 degrees north of east. Okay? So scale is real important when we talk about vectors, or when we talk about drawing vectors. Fair enough? All right. So we're going to draw a vector. The first thing you got to do, choose a scale. The second thing, pick a directional orientation. What I mean by that is the whole, like, maybe north, south, east, west. We won't always use north, south, east, west. Sometimes we'll just say left or right, up and down, stuff like that. All right, draw it to scale in the right direction, and label it. All right, so for example, we want to draw vector A. This little thing right here means, that little symbol means vector. A is a vector. All right, so unfortunately, I'm not going to be able to do this on the smart board here because I can't put a ruler on there. But what I would do first is choose a scale. And northwest, I might do step 2 first. And let's say that way is north and that way is south, east and west. So I know northwest, I really mean exactly northwest. It means that's going to be a 45-degree angle. So what I would do is sort of look from this sort of area down there to that area up here and say, how much space do I have in here? Come on, what are you doing? What are you doing? Ooh. Right on the board. There. How much space do I have from there to there? And I bet on your paper, if you were to choose a scale like this, 1 centimeter is 5 kilometers. Well, then what you could do is say, well, if I need 85 kilometers, how many centimeters long do I need? Well, you cross multiply, and you're going to get x's, I believe, 17 centimeters. Okay? What you do then, I might draw a nice horizontal, my ruler. I would take a protractor and measure 45-degree angle and draw my vector, 17 centimeters long, and then I would label it. There's vector A. Fair enough? Again, I didn't do this with a ruler and protractor. I actually want you to do it with a ruler and protractor. Got me? So this one, for you to do, I've given you a hint for that thing before where I said you have to figure out what quantities are vectors and what are scalars, because I've given you a different kind of quantity here. 275 meters per second. This is a vector. The question is, what do we call that quantity? What does B actually measure? 275 meters per second southwest. What are we saying that measures? That should go in your list, in your list of vectors. The question is, what quantity is that? What do we call that? Right? This one, what do we call that also? This actually we call not a distance, but a displacement. Or change in position. Question is, what kind is that? All right. Oh, so it says where it says you do that. Pick a scale, draw it correctly. Now, vector sums. Scalars are really easy to add. For example, what do we have in the first page? Oh yeah, we talked about volume, right? Well, we could say, for example, I don't know, 10 liters plus 2 liters is definitely 12 liters, right? You have 10 liters of water, you add 2 liters of water, no matter what, you're getting 12 liters of water. Agreed? Good. However, vectors can be added like scalars, but it's really not as simple. And here's a couple of examples to sort of lead you down that road. Let's say you're walking at a speed of, well, let's say that people walk at about 1 meter per second. That's how fast you walk. Relative, what we say is relative to the floor of an airport? Oh yeah, the people mover thing, right? You know those conveyor belts that you walk across on flat ground? And that thing, let's say that thing moves at, I don't know, 2 meters per second on its own. The question is, how fast do you end up walking? Well, and again, relative to the floor, to some dude who's just standing there in the hall. Well, you end up moving. Anyone? Anyone? Hopefully we can pick this out. 3 meters per second. We've just added 2 of these quantities. The question again is, what is this quantity we measure in meters per second? Now, if we look at the next one, what if you walk the wrong way? Ooh, look at this. Here's the phrasing, the new kind of phrasing of a question. What's the magnitude of your resultant velocity? Just giving you the answer. So velocity is kind of like what a lot of you, I bet, might have said is when you just hear 1 meter per second, which is okay to say 1 meter per second, that's what we call the speed. But velocity has a speed in it, which is its magnitude, and direction. So velocity is a vector quantity. That goes in your table on the front page. It's a vector. Speed by itself is a scalar, right? If you just say, I went 20 miles an hour, nothing wrong with that. I didn't have to say a direction. If I don't say a direction, well, it's a speed. If I do say a direction, then it's a velocity. Notice, I'm looking for the magnitude of your resultant, and this means total, or overall. What's the size of your overall velocity? The question really is, how fast are you going now? You walk the wrong way up this people mover. So the people mover is going, say, this way at 2 meters per second, but you walk this way at 1 meter per second. How fast do you end up moving? Well, you end up going that way at 1 meter per second. This is your resultant velocity. 1 meter per second to the right. All we really want, notice, all we want is what's the magnitude of it. So your answer is really just 1 meter per second. So notice, direction matters a whole lot. In one combination of velocities, we end up moving 3 meters per second. In a different combination of velocities, we end up moving 1 meter per second. So when we add vector quantities, of which velocity is 1, direction is really important. Okay? Here's a different one. Let's say this spider walks across the people mover at a speed of, I don't know, maybe half a meter per second. So here's the people mover. We could say that the spider walks this way, 0.5 meters per second. We could say that the people mover rolls that way at 2 meters per second. Now I want you to notice something. I haven't chosen a scale, right? But what I have done is tried to draw these sort of to scale, right? That's, 1 unit. Well, you know what? This should maybe even be a little bit longer. If this represents half a meter per second, and I want 2 meters per second, it should be 4 times as long. Yeah? So the question is, what's the spider's resultant velocity now? And really, I should say, right, relative to, I don't know, how about this? Location X. And here's location X, just a spot on the floor outside the people mover. Well, the spider walks across while the people mover rolls down. Hopefully you can tell that the spider ends up doing something like this. And I want you to notice that what we have here is we kind of have the 0.5 meters per second here, and we have the 2 meters per second there, or really we can actually make, like make that right triangle. And I bet if you know that this is 0.5 meters per second, and that's 2 meters per second, you could find the magnitude of that hypotenuse. I'm going to call that V R, resultant velocity. And I could say that the magnitude of VR, vector VR, is the square root of, how about this, the magnitude of the spider's velocity squared plus the magnitude of the people mover's velocity squared. Pythagorean theorem, yes? Or I'm going to drop that magnitude thing to the thing. V value is 0.5. Notice I leave the units in the work. 2 meters per second. Give me an answer. It's like 2.2. Right? Give me an answer. I don't have a calculator here. Now notice, this says what's the velocity? What's the spider's velocity? It doesn't say what's the magnitude of it. It says what's the spider's resultant velocity. So we need two things. Our total answer should be VR is some number of meters per second and at some angle. So I need, I don't know, let's say that angle. How do you know which angle you need? Let's just say, let's pick that one. You could pick this one if you want. I just chose this one. Tell me that angle. Show me some work and how you figured it out. It's okay? It's okay. Yeah. Let's go U. And then we'll start with this when I see you next. Okay, so finish this for homework. Should be real easy. Notice this part. Uh-oh. New quantity. 2 hyenas. That'll get you started tonight. If a lot of this was a repeat from class, oh well, my bad. I won't see you tomorrow. I'll see you on Friday. So don't overexert yourself with all the homework. And see you soon. Bye, folks.